Hello everyone. We are with Wojtek today, and he will be speaking on how to detect silent model failures. Oh, that seems like an interesting topic. Everybody wants to have a notification or update of when their models are failing or when there's something going on in their hands. So yeah, I think this would be a nice presentation. And Wojtek, over to you. And could you please start with a short intro of yourself?
Sure. Thanks a lot, Sanket. It's a pleasure to be here. My name is Wojtek Kuberski. I'm one of the co-founders of 9ML, which is a machine learning monitoring startup. We are operating across Europe, and what we're trying to do is basically protect the impact that your models have right now in your organization. I'm a technical guy. My background is machine learning. I did my master's in Belgium at KU Leuven. Then I started a consultancy. And then I moved to a startup, and I have to admit that startup life is really a cool life, but it's a lot of work. So that's me in a nutshell. Is it okay if I start the presentation, Sanket?
Yes.
Okay, perfect. So what we're going to talk about today is detecting silent machine learning failure. In other words, something that's called model performance monitoring. So without further ado, let's get going. So what's on the agenda today? We're going to start with the end in mind. So what happens when a model fails? And we're going to talk about what causes that, which is the concept drift and the data drift, and of course, the results of that, which tend to be disastrous. Then we're going to talk about, once we define concept drift and data drift, we're going to talk about how to detect it in real life systems. We're going to start with very simple techniques. We'll give a quick overview of simple techniques, and then we're going to go into some more robust approaches that tend to work a bit better. Then we're going to move yet a step further, and we're going to talk about using machine learning to predict performance and estimate performance using the signals from data and concept detection, even if we don't have access to ground truth data, which of course allows us to estimate performance of your machine learning models in production, and if something goes wrong, take actions. Then we're going to tie it all together. We'll go back to business, and we'll talk about how to make sure that the impact of your models is protected. And then we're going to have a very quick slide about how to implement it in your organization from a bit more engineering perspective. So let's get going. To set the stage, we're going to always think about an example use case. And this example use case is the loan default prediction case, where we take as model inputs the credit scores and customer information. And what we are trying to predict is whether a person defaults or not on a loan. So we're going to assume that this is a long-term loan when non-payment is defined. Basically, default is defined as a non-payment within first year. We, of course, need to have a business metric in mind, and this is going to be risk-adjusted return on investment. It's just a typical metric that people in industry use to measure the impact of their models. And then, of course, we need to have a technical metric that kind of links back to the business. And for that, we're going to, again, go with standard F-beta score. And for those of you who are not familiar with what F-beta score is, there's a quick definition here below. So that is an example that we're just gonna keep on referring to throughout the presentation. So let's start with what happens when models fail. Let's start with the data drift and define what data drift is. So data drift is simply the change in joint probability distribution of the model inputs. So let's assume that we have a reference period, which could be either the training period. One of the first periods in production can be a week, a month, an hour, depending on the volume of your data. And we have a current period. Current period is something that we are currently experiencing, and we want to see what is the performance and whether there is data drift during current period. And again, this current period can be last week, last month, whatever you choose. Here, there's just very simple visualization. When you see one-dimensional model input, and we have a density function here, and we see it's changing. So the more significant this change is, the stronger is the data drift. It's as simple as that. There is really nothing magical about it. So now let's talk about the second concept that we'll have to introduce here, which is the concept drift. So the concept drift is simply the change in the mapping between the target and the model inputs. So assuming that we have a certain number of model inputs, we're trying to learn the underlying real function that maps the model inputs to the target. And of course, this can change in time due to mostly external factors, things that are not observed in the data. So again, let's just imagine that we have a training data set and the real underlying kind of boundary between people who default and people who do not default is this gray line here. And as time passes, maybe because customer preferences change or they become more or less risk prone, we can see simply change in this boundary. So people who normally be unlikely to default, they become more and more likely to default, and we shouldn't be giving them loans. So that's constant. Again, nothing special, but there's of course a few intricacies here. So what we could have is kind of concept drift that is induced by data drift. So again, concept drift definition stays the same, but it doesn't necessarily be just the external factors that create concept drift. It can be also just the data drift within the data set. So imagine that we have two classes, right? People who will default, the positives, so the light blue here, and people who will not default, so the negatives, the purple color. And we train a machine learning model and we decide that the optimum boundary is here. And for our business, this is indeed the optimum boundary. But now, as time passes, we will see that there is more and more people who will not default. Maybe people become richer, maybe they become more risk averse. And that means that the actual optimal boundary can already change just because our metric is measured in a way and optimized for slightly non-linear behavior in the data. So we had the old optimal boundary here, but the new optimal boundary is here. So in that case, we should do something because our models are technically not providing less value, but we are not extracting as much value from our models as we could if we had properly monitored our machine learning in production. So that is kind of the overview of concept drift and data drift is. And now let's talk about slightly different view of machine learning that will help us later on have a kind of fresh look at concept drift and data drift. So we're going to talk about kind of the Bayesian network kind of approach to modeling real life behavior. And specifically, we're going to focus on the networks when we do not have access to every variable that actually causes the target or is caused by the target. So imagine network on the left is something that we would observe in reality if we had access to everything. This is the underlying ground truth of what is happening with the target. So maybe our loan default prediction is caused partially by how much people make, but maybe also by some internal psychological factors that, of course, we do not have direct access to, or some factors that we only have secondary access to, like here. So, of course, we cannot model it fully, and everything that's not modeled will be treated as a noise because we cannot really understand what's going on. So, to use a very simple, simplistic, even approach to machine learning, let's just imagine that we have these variables and they fit using arbitrary complex function, which could be a neural network or whatever you please, and they will try to fit into the model, and they will then create in practice, in production, they will create model predictions. And of course, we are losing some information here just because we don't have access to it. We cannot access it because it's not in the data. And this has some far-reaching consequences. So let's talk about data drift in this, looking from this perspective. So here the data drift is simply change in the observed variables. Because we define data drift as change in the inputs, it's of course something that we can observe. So far, so good. But now let's look at the concept drift. Before we're talking about the concept drift being the change in the mapping. But if you look at the left side here, the mapping can be fully defined by just looking at the input data and the output data, because literally nothing else here can influence the target. Everything else will be basically stemming from these three variables. So what you could say is that instead of looking at concept-driven change of the mapping, concept drift can be also defined as data drift in unobserved variables, because that will look as if the mapping between the model inputs and the target is changing, but actually the only thing that's going to change is how the unobserved variables behave and how they influence the target. And this is something we cannot observe directly, which is the main reason, of course, why it's so hard to predict the performance of machine learning models in production, and it's so hard to detect concept drift, which is going to be the main focus of the rest of the presentation. So let's start first quickly with data drift detection, as it is something that we need to build upon to really go to the end goal, which is performance prediction. Here, I'm gonna only focus on two kind of, maybe not main, but most adopted detections or methods to detect data drift. So the simplest one that has many shortcomings, but it's reasonably easy to implement, is statistical tests. So what we're gonna do is we're gonna look always at the reference period, so something that has happened in the past, and we know the performance of this past period, which could be last month, or it could be the first month of production, and or it could be even the training period, if we do not have access to any labels in production. And we will run simple, either univariate or multivariate tests on the input data, such as KS test, which simple visualization you have here. So basically, quick overview of what KS test is we're trying to see whether the reference period and the current period have statistically significant different distributions. So we're going to look at the cumulative probability distribution, and we're going to compute a statistical d-statistic, which is just basically the maximum difference between the height of this line and the height of this line for any of the x values. Very simple stuff. These are just statistical tests. For non-continuous variables, for categorical variables, we would use chi-squared test, which probably most of you are already familiar with. And there are some other approaches that sometimes try to take all the variables at once, but they still have very strong assumptions, such as maximum mean discrepancy. Unfortunately, I don't have a few hours to go in depth into all of those. So let me just say that these tests have lots of problems when it comes to the assumption. So simple thing is that if you just run KS tests on every single feature, you assume that they are independent, and you will not really look into how the correlations or dependencies between the input variables are changing, which could, of course, very strongly influence the performance of your model, because they are also modeled by more advanced machine learning systems. So now we're going to look at the second part, which is slightly more advanced, and in our experience tends to work reasonably well on all kinds of data. So we're going to look at measure of a data drift, which is reconstruction error of either dimensionality reduction techniques, manifold learning techniques, or some same-to-same mappings like variational autoencoders. So what we're going to do, let me take a variational autoencoder as an example here. So what we're going to do is we're going to take the original data set, so the light blue here, the reference period, and we're going to train a variational autoencoder on it. Which means that, of course, we create a bottleneck in the data. The network has a bottleneck, and it's trying to learn compressed representation of the data. And this compressed representation of the data, of course, encodes the structure of the data, because we cannot have a general compressor that works on all kinds of data. The compression is only possible if either the data is redundant or if we can model the structure of the data. So here we will use the reduced space, and then we're gonna go back to the original space. So we're gonna reconstruct the inputs from the inputs using, of course, the bottleneck. And on the reference period, we expect it to work reasonably well because the model trains to optimize. And then we're gonna use the same network that is trained on the reference period, and we're gonna try to reconstruct new inputs. And if these inputs are reasonably close and the manifold on which the data lies is the same or very close to the manifold that the reference period data lies, then we should be able to reconstruct the new data without too much error. So the reconstruction error is going to be low. However, if the data has changed and the manifold is different, then it's going to be quite hard for the network to reconstruct the data correctly, and we're going to expect high reconstruction error, which leads us to just having reconstruction error as a good metric that not only shows whether the data drift exists or not, but also the magnitude. And let's talk about PCA as an example, another example, and let's go a bit more in depth again. So let's start with quick assumptions of PCA. So first of all, we need to assume that the linear data transformation is appropriate for our data set. We need to assume that the mean and variance are reasonably sufficient statistics to represent the data, and that orthogonal principal components are, again, a reasonable transformation of the data. It doesn't need to be perfect, but it needs to be good enough. As you probably know, in practice, PCA is a reasonable, again, dimensionality reduction technique, even if some of the assumptions are violated. So we're going to do what I just described. We're going to train the PCA. We're going to fit the PCA on our reference period. And then we're going to use this fit PCA to try to reconstruct the data over time. So imagine that we have a training period, we have validation period, and we have pre-production periods. And what we can expect is that as data slightly changes in time, we're going to have some variance in the reconstruction error. It tends to increase immediately just because there might be some kind of randomness, unobserved things in the data that influence this randomness. And then it's going to stabilize until there is data drift. And funny thing that we observed is that, of course, as the reconstruction error increases, we can expect data drift. But also, if the reconstruction error decreases, it means that data becomes maybe even more linear or more condensed, which actually results in decrease in reconstruction error, which is also a very strong signal for data drift. This is simple, but reasonably well-working data drift detection technique that can kind of serve as the first idea if you were to implement data drift detection yourself. That is something I would recommend doing. It's simple, it doesn't take much time, it doesn't take much optimization, and it will get you, let's say, 50% there to really be good at data drift detection. But of course, data drift does not necessarily mean model failure, and let's talk about it here. So we have 4 visualizations here. The first 2 left ones are just example of the training data and the production data. And if we see no concept drift, it's not induced by data drift in any way, then we can expect our model to perform still reasonably well, even though there is, for example, less data in this part compared to this part now. But if data drift in some way induces concept drift, that means that the decision boundary changes. So the decision boundary that was trained by the model is no longer appropriate, and we can expect the model to make more mistakes. So that can result in model failure. And of course, we could just, instead of doing all that, we could just measure the performance if we had ground truth. But the thing is, we very rarely actually do have full access to ground truth. And there's 3 reasons for that. So first of all, in automation use cases, so in the case when trying to automate some kind of work that was done by a human, that's the point of machine learning use case, to not have to do it again manually. So the ground truth that people used to provide manually will no longer be there. Of course, there are spot checks, but we can expect at most few % of the data to be available. Then, using our example use case, the ground truth tends to be delayed. So in this case, we have to wait 9 months to really get the ground truth about whether people defaulted or not. And that is something that's not acceptable. We cannot really have model running for 9 months, giving loans to people without really knowing what's going on and whether it's performing well or not. And even if we do have labels quite shortly after the prediction is made, they tend to be incomplete. Imagine a churn model when you actually never know whether the person would have churned if you hadn't acted on the churn prediction. When the person is predicted to churn, there's marketing campaigns, maybe some discounts applied, and this person maybe doesn't churn, but you will never really know whether this person would have churned if you haven't had acted. So the labels are rarely complete. And because of that, we need to try to estimate performance of machine learning models even without access to ground truth, because we never do have full access to ground truth. So how do we go about it? First thing we could do is we can just look at the regions of the data that the model is performing well versus the regions of the data where the model is not performing well. So on the first plot on the left here, we see the training period. and the dots are just data points. And the violet place in the data, the violet blob, is the place where the model is predicting very well. It's very certain about predictions, and it generally performing well. The green part is the place, the region of the data when the model is not performing well. And as time passes, two or maybe other things can happen, but of course there's two example things that can happen that will actually influence the performance of the model. One of them is, let's say that the data moves from the region when it's performing, when the model is performing well, to the region where the model is not performing that well, which we can detect, and then we can reasonably say, or with quite high certainty, we can say that the performance of the model has decreased, and we can even measure this effect. Another thing we can see is that if there's data drift from the regions when the model really knows what's going on, there is a lot of data to train, to the regions in the input space when there's not that many, when we didn't have access to many training examples, like here. And then we cannot really say what is the performance of the model. We just can say that we don't know what's going on. And that is something, so the uncertainty of our performance has increased significantly, which of course is also useful. Now let's look at concept drift prediction, and I'm just gonna go over it very quickly, and I will cover the easiest way of doing that, which is, let's assume that, of course, for certain periods of production or certain types of data, we will have access to ground truth. We can measure it, and then we can use time series techniques to try to extrapolate it in the future. And that, combined with our data-driven detection methods, tends to give a pretty good view on performance, even if we don't have access to ground truth. So now let's talk about actually putting it all together. So what we do, and probably that's one of the more robust ways of detecting performance, is that we put all the data drift signals, we put our predicted concept drift, and we're also going to try to model kind of the real life from Bayesian perspective. We put it all in kind of the overarching machine learning model that then it tries to predict performance of model in production. And if you take all of these ideas tied together as features in the model, then the model can pick the ones that are most relevant. And that increases kind of the robustness of our machine learning prediction, performance prediction system. But now let's say we all have this, we can predict performance. And the question is, so what? So how do we actually turn that into something that provides value to the business? So the first thing we should do, I'm just gonna walk you through the steps that are necessary to provide value. First, we need to predict or measure the performance on the entire population level or the entire sample level that we have access to. And then we should also look at the segments in the data that we particularly care about. Just because the performance on population level is reasonably stable doesn't mean that there might be some, there might be some segment in the data that we particularly care about. Maybe these are people that provide more value to the business. Maybe these are people that are very important because they're outspoken. We need to look at these segments and we need to see how these segments perform. So we're going to do the exact same thing that I described again at segment level. And then we're going to see whether these things work or not, whether the performance at every segment is still reasonably high or whether it has deteriorated. And then what we should do next, we know what has happened, but we don't really know how and why it happened and what to do to fix it. So then we would need to go to the root cause analysis, and then we would like to recommend or suggest corrective measures to really fix the problem, which might be as simple as training and as complex as redeveloping the model, because maybe the relationships that the data exhibits are no longer can no longer be modeled by the existing machine learning pipeline. I would love to go more in detail in the root cause analysis and how to suggest corrective measures, but it's unfortunately only a 20-something minute presentation, so I can't do that here. So now, slowly wrapping up, let's talk about how to implement it in your organization. So quick overview of how normally machine learning works. So we have a business process, whatever it might be giving loans to people. We have the customer environment that you as people who create model performance monitoring would be serving, which is basically data scientists that develop these models. And we have the model input, we have the training data and the metadata and the model output. And ideally, we would also like to have access to the repository with KPIs, with the ground truth, and maybe some other downstream data from that results from the business process and the actions that are taken based on machine learning model recommendations. And then at the end, we would have our performance monitoring system. When we have our processing pipelines, probably some notebooks to really show data scientists what's going on so they can quickly access that. We'd like to have integration APIs and all the other engineering things that are necessary there. And of course, we'd like to track it in time just to see how it performs in time, whether we should act or it's still okay. So these things tend to be stored in some kind of time series database. And then we give it to business users, data people, and machine learning operations teams so they can act on it and make sure that the impact of machine learning models is protected. And that's basically it. Here there's a few resources. I will not go over them. I'm going to show the presentation afterwards, of course, so you can look at them if you are interested. And that's it. Thanks for listening. And if you'd like to learn more about it, feel free to either email me, add me on LinkedIn, message me on LinkedIn, and I'm happy to answer any questions. I will also be in the Slack chat after the presentation. So let's chat there. And thanks everyone for listening. That is it.
Thank you, Wojtek, for the presentation. It was a wonderful one. And Wojtek, we have a question. I think it was asked earlier in the presentation. I'm not sure if it was covered or not, but I'll still ask you. The question is, the drift is because of external factors or not?
So maybe I'll go back to the relevant slide and talk about it quickly. So what you can see here is basically Bayesian network, right? And these are the external factors. These are the things that we cannot see. And these are the things that we can see. So they are just features in our data set. And data drift, as normally defined, is due to change of the observed variables, our features. And concept drift, so the change in the mapping, as you would see in between the model inputs and the target, is normally due to the unobserved variables. But of course, let's say that this unobserved variable changes. It is quite likely that it changes because this variable changes. So there is a certain relationship or correlation between the data drift that we observed and also concept drift that stems from that. So it's always basically almost always a mix between observed internal factors and external factors. If you are really unlucky, it might happen that there is some external variable that you cannot observe with in any way. It's not correlated with any of the things that you can observe. This variable changes influences the target, and then you would just see concept drift without really seeing any data drift. That is something that's possible, especially in machine learning systems that are barely better than random. Because if machine learning model has very high metrics, it generally means that most of the information in the data that can put information in the world that can potentially impact the target is already captured by your system. You have access to all important variables. But if your model is barely better than random, it means that there's a lot of unobserved variables that influence the system. So then you are also more likely to experience concept drift. I hope that answers your question.
Yeah, so we do have a couple of questions, more than a couple of questions for you. The other question is, can you automate the model correction?
Sorry, come again?
Can you automate the model correction?
Yes, so this is something that kind of comes downstream from model monitoring. It's something that you can, I would say, augment, and we are quite far from automating. And the way we go about it is that you can easily integrate, either our solution or something that's homemade, where you get signals for performance, the performance. You can have also the confidence bands on the performance. And once it crosses certain threshold, when you know that the impact of your model is at risk, you can trigger retraining. And if you have good root cause analysis and recommended actions, you can decide what has exactly happened, what variables changed, and then you can take the actions. Sometimes the actions can be taken fully automatically if it's simply training, or maybe dropping some data from the training data set and training, or maybe doing some kind of correction, some kind of covariance shift in your training data to account for data drift. These systems will be extremely complex, but you can automate them. But sometimes, if the root cause of the problem is the fact that there is a change in unobserved variables, you would need to go and try to find what are other things that are changing so I can fix my model. So in some cases, you can fully automate that. Sometimes you would, for example, like to trigger spot checks in your automation system. So then people go and manually inspect the data, provide new labels, and then you retrain. And then everything apart from actually doing spot checks can be automated, but the spot checks themselves need to be manual because you need to have ground truth that's provided by humans.
All right. Thank you, Wojtek. So we are over the time, but I can still take one question. So the next question is for Ian, and the question is, which domains frequently show concept drift?
Yeah, that's a great question. That's a really interesting question. So from my experience, mostly everything that has to do with tabular data will experience more drift because you operate in high noise kind of regimen. If you work in computer vision, the cat detection is a cat. Cat is always a cat, and cats will continue to be cats. If you try to detect something in the image, as long as it keeps on looking the same to humans, it will keep on looking reasonably similar to the machines. However, if you work with anything that has to do with clients, anything that's customer facing, you tend to experience a lot of concept drift and data drift there as people are changing, their preferences are changing, their behavior is changing. So that I would say is kind of the domain that experiences the most data and concept drift. Finance, commerce, anything that deals with people really.
Thank you for the answer, Wojtek. And I think we are almost at the time. So I would like to thank Wojtek for coming today and sharing your knowledge with us. And it was a wonderful presentation.